Okay, so today's lecture, we will continue on signal properties. Then we expect to start unit step and ground signal. And the readings associated with today's lecture, which is from page 11 until 21. Don't forget Friday, next lecture, the homework due, homework 1. So it will be due at 10 a.m. So you need to submit it before 10. It's already posted, and there is one PDF file posted in homework 1, and including also page 111, page 26 of the textbook. Then the reading for the also Friday, it is from page 16 to 21. Make sure also to read this before Friday lecture. Then in Monday lecture, the reading from page 30 to 35. Wednesday lecture, it will be due for homework 2. Homework 2 will be probably 116, 121, 120, also 121 part A, C, D, 128 A, B. Also, this is also written on the homework assignment, so you can go to Canvas, homework assignment, so you can see the information about homework 1 and homework 2, what you already need to do. Okay, any question on homework? Okay, so let's continue on signal properties by doing now the time reversal. So time reversal means there's a negative sign on the time. So if we can say, for example, y of t equals to x of negative t. So in this situation, what will happen? Let's assume the following waveform, and we need to apply the time reversal. So I'm going to assume the signal x of t like this. Now we need to find x of negative t, which is y of t. So how can we do it? Basically, you will reverse the time. So like make it like a mirror. So it will look like this. So this is x of negative t. So again, you need to make it like a mirror. Mirror it this on the y-axis. So here for time reversal, basically mirror on y-axis. Okay? How about if I say z of t equals to negative x of negative t? Now we are not only having a time reversal, we have also a magnitude reversal. So whenever we have a magnitude reversal, you will flip on t-axis. So I will say because of this negative sign, you will do a mirror on t-axis. And since we have two negatives, so we will do a mirror on the t-axis like this. Then this is negative x of negative, which is this is 0 of t, and that one is 1. Okay? Does this make sense? Another example. So this is x of t. Now we need to make negative x of negative, x of negative t. To do this, you need to mirror the waveform. So basically, it will be like this. Okay? Now, we need to think also on something else, like when we have both time shifting and scaling and reversal. So if we have multiple things, what do we need to do? So for example, when we have y of t equals x with at minus b, how can we treat with these type of problems? Basically, we will see that we have scaling, because we have a for the scaling. Then we have b, this is for shifting. So when we do before our problem or the examples, we used to do scaling alone, shifting alone. Now when we have both, what we need to do is we need to follow the following procedure. So basically, you need to simplify the procedure. We need to simplify by making the factor of t as 1. So y of t will be x of a, then between brackets t minus b over a. So note that the factor of t is only 1. That's why I take a as a factor. Then it will be t minus b over a. Then what we need to do is to assume z of t equals x of a of t. So as a result, what will happen? Y of t will be x of at minus b over a. Now in terms of c, it will be z of t minus b over a. So now with this assumption, the problem will be easier. So what we need to do first, we can do two procedures. Step number 1, we will apply scaling, which is we will apply a to get z of t, such that z of t equals x a of t. This is the first step. The second step, we will shift z of t by b over a. Then forget y of t, which is z of t minus b over a, or in other words, x of a t minus b over a. So therefore, in order to plot the waveform for these signals, the first thing, let's assume z of t equal x a of t. Then after that, we can make our scaling first. After we make the scaling, then we can do the shifts. Okay, let's see an example to get a clear picture. Now, let's assume we have the following waveform. Given x of t like this. Such that this is 0, this is 4, this is 2, then here let's assume the magnitude is 1, here is t, then this is x of t. So the question is, since we have given x of t, now we need to plot y of t equals x of 2t minus 1. How can we solve this question according to the procedure? The first thing, try to make the factor of t as 1. So basically, we will say y of t, x, we would like to make the factor of t as 1, we will take 2 as a common factor, then it will be 2, or 2 between brackets, t minus 1 over 2, minus 1 half, Okay? So multiply 2 this time 2t, then 2 minus 1 half will be negative 1, then that's it, that's fine. After that, we will define z of t equals x of 2t. As a result, y of t will be z of t minus 1 half. Okay? So we will use the first equation for step 1, the second equation for step 2. Okay? Now for the first equation, step 1, where z of t equals x of 2t, since 2 larger than 1, therefore we will shrink. It will be as shrink, not as expanding. If t less than 1, it will be expanding. That's what we discussed last lecture. 2 larger than 1, then the waveform will be shrinked. So what will happen is, I'm gonna make this plot. And since the factor is 2, so shrink by 1 over 2, by 1 half. Then, shrink, if this is only in time axis, of course. So here is t. Now we need to plot z of t. So it will be here, time axis 0. Here it was 4, now it will be, instead of 4, it will be 2. That one was 2, now it will be 1. Okay? Did you get it? Or in other words, let me do it. I'm going to plot x of t and I make the guidelines. I'm sorry about that. So it can be, you can get a clearer picture. X of t was here at 0, 2, 4, 0. Then I can make the guidelines from this. Then what else? So this is x of t. Now by drawing z of t, we need to shrink it by 1 half. So here is 2, 4. This is the guide, and we need 1 here. Here is 1. So it will be shrinked such that those remaining zeros, it will be shrinked. It will reach the top at 1, then back to 2. This way, and the magnitudes here, the magnitude was 1, the magnitude no change. No change on the y-axis, the only change on time, because we do everything in time. Now the next thing, after we did the scale, because x of t, z of t equal x of 2t, now the next thing we need to apply the phase shifts. So the shift, the time shift, we have y of t equals to z of t minus 1 half. So we need to shift it 1 half. Therefore, let me look at step number 2. Y of t equals z of t minus 1 half. Let's look inside the brackets. T equal 0.5. Since it's positive, then shift right. So we will shift right. So what we will see instead of 0 will be at 0.5. Here is 0.5, here is 1, 2, 4. And what we used to see in 1 will be at 1.5. 1.5, then here 2.5. So all our concern is to look at 0.5, 1.5, 2.5, because everything will be shifted. So instead of 0, 1, 2, add 0.5 to it. By adding 0.5, it will be, because it's shifted left, shifted right, 0.5, then reach at 1.5 maximum, then go back to 0 at 2.5, and remains 0, and this remains a magnitude as well. Okay? Then that's how we do the shifting. The first thing, assume z of t equals x of the scale, then do the scale. After that, you can do z y of t as the shift. Okay? Is this clear? Now you need to keep in mind some important thing. You need to do the steps or the procedure in order. So, you need to do, you need to make the steps one first, then step 2 second. So the order matters. So what I would say y of t equals to x of at minus b. So step number 1, you will say z of t equals x of at, then do it. Step number 2, you will say y of t equals z of t minus b over a. That's what keeps me. However, if someone say, for some reason he said, I'm gonna make step number 1 as phase shift, like I'm gonna assume z of t equal x of t minus b over a, then step number 2, I will say y of t equals to z of at. So if you do the opposites, this is wrong. Well, the first one is wrong. So the order is important. Why? What's the point? Because if you do this, this is actually equals to x of at minus b over a. And that's not what we want, because our target is to get x of a then t minus b, which is equals to x of at minus b. Okay? So if you flip those, then this will yield to invalid results. This will yield to different function, which is x at minus b over a, while our target is to find x of a between brackets t minus b over a. So anyway, just make sure the order is fine. That's my biggest concern. Now some other signal properties. Some signals, like, especially in some signals, not for every signal, which is something we call symmetry. When we can say these signals are symmetrical. So what do we mean by symmetry? Which is there is another waveform very similar to it. How and why? So let's plot this example. Now look at the right-hand side and left-hand side of this sequence. The right-hand side and left-hand side are identical the same, right? So in other words, I will say x of t equals to x of negative t, right? So this is symmetrical. Since this is symmetrical and they are equal to each other, we will call it even symmetry. So keep in mind, this is symmetry with y-axis. Right hand side and left hand side are equal to each other, exactly the same, so these are symmetrical. Now there is another type of symmetrical like this. Okay, so this is x of t. So in this situation, x of t does not equal to x of negative t, but it will be the negative sign, negative x of negative t. Okay? So what's in the left hand side and the right hand side are just reversed. So in this situation, it's symmetric, but this thing we will call it odd symmetry. Odd symmetry. So basically, this is symmetrical on y-axis, then symmetry, or this is flipped to y-axis, then flip it to t-axis. So we'll do it twice. Basically, this is the signal. Flip it on y-axis, you will get this. Then flip it on t-axis, you will get this. So by looking at those, this will be symmetric. Okay? Now, I want to give you some examples. Like, classify if this one's symmetrical or asymmetric of these functions. And if it's symmetric, classify is it even or odd. So let's look at f of t equals to cosine 2 pi t. Recall, odd symmetry, x of t equal negative x of t. X of negative t. While even x of t equal x of negative t. So how can we check is it symmetry or not? Basically, we will find f of t first, then find f of negative t, then we will compare. That's how we find. So f of t equal cosine of 2 pi t, f of negative t, cosine of negative 2 pi t. Let's find a value. Let's assume, for example, t equal 1. So f of 1 will be cosine of 2 pi, cosine of 2 pi, which is cosine of 360. This is equal to 1. Then f of negative 1, which is cosine negative 2 pi, negative 2 pi in radian 360, f of negative, or cosine of negative 360, which is 1. Since f of 1, f of negative 1 are equal to each other, therefore, is it even or symmetrical? Is even symmetrical or odd symmetry? Even function or odd function? Even. Even symmetry or even function. Or we can prove this in different way by looking at the waveform. The waveform of sine or cosine starts here from 1. Then we will see, look at right hand side, then look at left hand side. They are exactly the same, right? They are like mirroring on the y-axis. Therefore, it is even symmetry. Now another example, which is f of t equals sine 2 pi t. Let's prove this in the waveform, then we will do it in math. So in the waveform, this is how the sine looks like. Now the question is it even or odd? Or is it symmetrical or not? It's symmetrical. Is it odd? Yes. Why? Because it's the opposite. Just flip it on the y-axis and make a reverse. Therefore, also we can prove this in math as by finding f of, for example, negative 1 over 4, which is sine of 2 pi times negative 1 over 4. In other words, sine of negative pi over 2 sine of negative 90 equal to negative 1. While f of 1/4 equals sine of 2 pi times 1 over 4. Therefore, it will be sine of pi over 2, which is sine of pi over 2, sine of 90. Therefore, sine of 90 degrees being equal to 1. Therefore, f of 1 over 4 equal negative f of negative 1 over 4. Then we will say it is right. This is right. Okay? Any question? Now another thing, we're still like in the signal properties, is called periodic. Periodic signals. What does periodic signal means? And how can we know the signal is periodic? Basically, periodic signal means a signal that repeats itself continuously and exactly every specific period of time. Function that repeats itself every specific period of time. Here is a demonstration example. When we have a function like this. I'll continue forever. Continue forever. Okay, so regarding to the so in periodic signal, this is a special type of signals that repeat itself every specific period of time, and basically you can look at the startup of each the beginning and the startup of each signal. You see it repeats itself, and the time between here to here we call it TO, and the same here, time between both ends equal TO, the same time, TO, TO. So we realize it is repeating itself every period of time. That period is called TO. So in other words, in mathematical expression, we will say that x of t plus n TO equals x of t, such that n is integer, TO is period. So n is integer, it can be n equals 0 or plus minus 1, plus minus 2, etc. Okay? In other words, I will say that x of t equals to x of t plus TO equals x of t plus 2TO, etc. Or x of t minus TO, x of t minus 2TO, etc. That's how I can judge this is periodic. Again, TO is called fundamental periodic. Which is constants for every function, for every repetitive form. So when you see anything comes in repetitive form, it's being repeated forever, this is called periodic signal. Okay? Something happening forever. It's not happening once and go. Here's an example. Verify periodicity. Make sure is these functions periodic or not. Periodicity. So the first function, f of t equals e power negative 2t, t larger than or equal to 0. Is this function periodic? Yes or no? Actually, when we look at the waveform, it is exponential. Something like that, right? So it's not repeating itself in every specific period of time. So of course it's not periodic. How can we prove this using math? Basically, in periodic, we will say, let's check, does f of t, is it equal to f of t plus nt? So let's substitute. Does e power negative 2t, is it really equal to e power negative 2t negative 2 t plus nt? Or in other words, e power negative 2t times e power negative 2 nt. Now, I will say e power negative 2t, e power negative 2t, we can divide by 1. So now, is it really equal to 1 e power negative 2t? Is it really equal to 1? As we know, t must be integer or positive number, actually. Positive because it's time. And integer, 0 plus minus 1, plus minus 2 and others. The only situation e power something equal to 1 when it's e power 0. So if, when n equal to 0. When n equals 0, then yes, 1 equal e power negative 0, that's fine. If n equal 1, e power negative 2t, is it really equal to 1? How about n equal negative 1? Or is it even equal to 1 if it is non-zero? No. So there's no way for this function to be periodic. So it's, of course, it is non-periodic. Okay? Any question? How about another function? F of t equals to cosine t. Now let's check, is it periodic or not? So then let's check, does f of t equals f of t plus 2 nt? Let's substitute. F of t, here it's cosine t. Is it really equal to cosine of t plus 2 nt? Okay, how can we do the cosine? Recall the identity. Cosine alpha plus beta equal cosine alpha cosine beta minus sine alpha sine beta. I think you know this from calculus. Cosine alpha plus beta equal cosine alpha cosine beta minus sine alpha sine beta. So now, does cosine t, is it really equal to cosine t cosine 2nt plus sine t sine 2nt? Is it really equal? Okay. How can we judge? Basically, nt, which is the total period, or t, the period as overall, for the trigonometric function, 360 degrees, or in other words, 2 pi. Okay? So, When we say, is it 2 nt? I think it should be nt, not 2. Nt. Okay. So t equal 360. So I will say that thus cosine t equal to cosine t cosine 2 pi n plus sine t plus sine 2 pi n. Now n can be any even number or any integer. So cosine of 2 pi or 2 pi times 1 or 2 pi times negative 1 is all the same. So cosine of 2 pi is what, or cosine of 0 actually, of 360, which is the same as 0, is 1, right? Cosine of 0 equals to 1 plus sine of t. Sine of 0, sine of 0 is 0. Now, this term will go cancel each other. This is 1 will be cosine. So cosine t equals cosine t. Then that's fine, that's correct. Therefore, we will say it's periodic. Okay? Yes?
Can you choose whatever you want t to be, or is there like a set thing?
Maybe for n?
For the value of t period?
Yeah, the t.
360, it can be anything.
It's t here, we choose at 360 because it's periodic, or it's sinusoidal function. Then the period for any sinusoidal is 360 degrees. So this is constant. But the thing is, you can choose whatever n you want. Here I choose n as 0, therefore it's cosine of 0, sine of 0. While you can choose it as negative 1, so it will be cosine of 360, cosine of negative 360, something like that. Then you can choose any n you want, but not t. T here is fixed, 360. Okay? So as a result, we can see that the cosine and even the sines actually will be periodic sequence because it's repetitive sequence, so they are repeated themselves. Let's see another, or let's look at the waveform. X of t equals a cosine of omega t. This is the overall waveform of the sine or cosine. I think you are familiar with this from circuits class. So we used to say A as amplitude, omega t here, or even like I would say I can add plus alpha or plus theta, something like that. So omega t here related to angular frequency. Omega is angular frequency such that omega equal 2 pi times f, omega in radian per second, while f in hertz, and we know hertz, which is cyclic frequency, which is basically cycle per second. And we, to complete one cycle, we need to have 2 pi. This is in radian, or 360, this is in degrees, whatever you use. Then we have theta, this is phase shift. If your standards in radian, then you need to put it in radian. If it is in degrees, then you need to put it in degrees, depending on what's your expression. Now, we need to know that the period fundamental period which is TO equals 2 pi over omega. Then it will be 1 over f. That explains in the previous example why we assumed it is 2 pi. In the previous example, last example, we have cosine t. So in this situation, omega equal 1. Therefore, TO equal 2 pi over 1, that's equals to 2 pi. That's why in the last example we assume TO as 2 pi or as 360 degrees. Okay? However, if we have, for example, another example like cosine 2t, here omega equal 2, therefore the period TO equal to 2 pi divided by 2, then pi. So if you have cosine 2t, then you need, in the previous example, let's assume it's 2t, you need to substitute the period as pi, not as 2 pi. Okay, any question? So keep in mind, how to choose t is very important. How to choose TO, which is 2 pi over the angular frequency, or 1 over the frequency. If you know the frequency, then probably done 1 over the frequency. If you don't know it, then it will be 2 pi over the angular. Any question about this? Okay, so here there is in the MATLAB code, you can find it also in Canvas, that code. Basically, in plotting the sine or the cosine with form. So here's the overall code. This can be sometimes helpful for you, and as a guidance if you need to plot any sinusoidal or any periodic functions. So you need to here we define the amplitude as A, then we need to define the frequency. So here we call it, for example, 1e power 6. E power 6 means 10. Sometimes as, instead of say 1 times 10 power 6, as a shortcut we used to say 1e power 6. Okay, that's in MATLAB. So E here does not mean exponential. If we need to use the exponential, we will say EXP. So here minus 1 times 10 power 6. Which is 1 megahertz. Then theta d is the phase shift. We call th as theta, d as theta d. Then the period is 1 over the frequency. If we need to assume any theta d, we can assume it. So for example, when we convert in the expression, let me make it so the first thing in the command here, t equal 0.01 times t. So I need to plot 2 cycles. So here we have 2 times t because I need to plot 2 cycles. Then the other thing, which is I use 0.01. This is as a time step. So as a resolution, in other words, as a resolution. So the larger time step, the lower resolution. If you make it 1, you will have a poor graph. If you make it 0.1, better graph, but still not accurate. If you make it 0.01, this is also better graph. If you make it smaller and smaller and smaller, you will get a higher resolution. So for this 0.01, we get this waveform. But if you zoom it, you will see some errors here. But the lower step size, the better accuracy will be. Then, that's we define as a set of data, then we can find x of t. So x of t, 2 pi cosine 2 pi f t plus theta. Keep in mind, everything must be here in radian. That's why when we make theta times pi over 180, because we convert everything to radian. Because here, theta d in degrees, this theta in radian. So we converted the phase shift in radian. Then here we are using the angular frequency, 2 pi f t. Okay? Then again, if you are using radian, don't forget to convert theta to radian, and we will do it everything in radian. However, if we need to use this in degrees, there is an internal command in MATLAB. It's called cosine d. If we are using cosine d, like x equal a times cosine d 2 times pi times f times t, then plus theta, you will use degrees, not theta. Okay? So there's a command called cosine d. This is only for I'm using in degrees. So the default in the MATLAB is radian. However, if you need degrees, just add d to the cosine, then it will be degrees. Then how to plot this function? Let's just plot t, x, like as we see in this plotting command. Then we set an axis, and the grid is on, basically to make these guidelines, as we see here. So and so on. Then we label time axis and we label x axis. So this can be a demonstration for you. This can be helpful in how to use the MATLAB. So I encourage you to try this as well. And even I think in the MATLAB projects one, I think maybe it will tell you to refer this code. So anyway, this is something important I need to. Now let's keep going to the unit step signal. Unit step signal, as a shortcut, we will call it U. And actually, U of t is what? In real life, it is 0 when t less than 0, 1/2 when t exactly equals 0, 1 when t larger than 0. So the waveform is actually like this. So here we have delta over 2, we have negative delta over 2. But actually, delta is very small. And it will be 0, close to 0. So as a result, we will not plot U of t like this. We will plot U of t like this. Here's 0, here's 1. So delta, the period, is very small because it's equal to 1/2 exactly at t equals 0. No other value. So in order to avoid all of these confusions, we will not talk about what happens at exactly 0. We will talk about what happens after, before 0 and after 0. We will not look at what happens exactly at 0. So we will say U of t equals to 0 when t less than 0, or equal to 1 when t larger than 1. That's what we will use. Use this. We will not worry about the 1/2. So how about if I multiply a function like k U of t? What will happen? If less than 0, yes, less than 0, it will be 0, k times 0, 0. If it's larger than 1, it will be k when t larger than 1. So what's the point of this function? Why I need to use this function? Actually, we can use it as a switch. U of t is used to turn on or off any signal. So I would say x of t times U of t equals to 0 if t less than 0, x of t when t larger than 0. So let's assume we have the following signal of x of t. Now, if I need to plot x of t, U of t, then only we will worry about what's happening after t larger than 0. What the rest will discuss. Okay? Because it will cancel each other. And this is something very similar, or let's recall in the circuit analysis, sometimes we use the switch on the signal. So this can be replaced for a switch by using U of t. Switch on or off at t equal TO, then we will say U of t minus TO. We can replace it. That's how we switch the signals. Then we will continue on it next lecture. So see you later.